Well, thank you very much. So I'm grateful to the organizers for inviting me here. One of the many things I admired and appreciated about Jean-Pierre was his willingness to talk to algebraic geometers like me that are transcendentally challenged. And so in the same spirit, I hope you'll forgive me for giving a talk that's rather far on the algebraic geometry side of the spectrum. I'm going to talk about a sort of a series of questions and ideas that people have been thinking about for the last few years that so far haven't really made good connections with the transcendental side of the field. So rather than talk about any specific result, I'm going to try to survey the area, mention some of the open questions in the hope that people with more transcendental skills can help us out. So that's the plan. So to start, let's let X be, well, we might as well make it smooth. So a smooth, irreducible projective variety over the complex numbers. And let me recall that, let's see, how can I, well, okay. So let me recall that first, a very important notion in algebraic geometry is what it means for such a variety to be rational. So X is called rational if it's birationally isomorphic. So birationally isomorphic to Pn. So this is a very classical and important concept in algebraic geometry, and there's been a huge amount of work in progress in the last decade or two about the problems of properties of rationality and what varieties are rational or not. But I'm going to sort of talk about something much more modest. Of course, most varieties aren't rational, and so I want to sort of the basic question, at least for the beginning, I want to talk about is so if X is so how can we, assuming that we know for some reason that X is irrational, so that X is known to be irrational, and that's already quite. How can we measure and control? So how can we control and measure? Let me say measure how irrational it is. So this is going to be the first part of the talk. Okay. So if you have a variety, most varieties aren't rational. So if you have a variety that you know for some reason to be irrational, how irrational is it? Well, okay, so there's the sort of the beginning case where I think most people will agree on what the answer is. So let's assume that, that X is a compact Riemann surface. Then the natural way to do this is what's called the ganality. So recall that the ganality of X, so then the ganality of X, it's not my favorite word, but is by definition the least degree with which any Riemann surface is a branch covering of the Riemann sphere. So the ganality is the least degree of a branch covering from X to P1. Okay, so, and this turns out to be the very natural, the most natural invariant. So for example, if you've taken a classical course on Riemann surface theory, you know that the most special curves beyond rational ones are hyperelliptic curves. So those are the ones that have ganality too. Those are things that are degree at Pn. And so the question is, in higher dimensions, what can we do to sort of generalize this? So I want to start by, there are lots of invariants you could define, but I want to give, I'm going to focus here on 3 of them. So now let's go back to the case where X has dimension n. So the first, in a way, the most natural one is what people call the degree of irrationality of X. So this is just the exact analog of the ganality of a curve. So it's the minimum of all deltas, positive deltas, so that, yikes, I think I'm gonna, so that there exists a rational covering from X to Pn. So all these invariants are supposed to be birational invariants. So we're going to always allow ourselves to look at rational maps rather than morphisms. Okay, so when X is dimension 1, we get back to the old definition of gonality, and so clearly the irrationality of X is equal to 1 if and only if X is rational.
Rational covering of degree delta.
Yeah, thank you. Thanks. Degree delta, yes, that's, thanks. So if X is birational to Pn. So the degree of irrationality is 1 if and only if X is rational. So this is in some ways the most natural invariant, but it's also not so easy to control. And so there's some other invariants that people have looked at that kind of reduce the question to curves. So you look at what kind of curves you can cover X with. So the next invariant is what people call the covering gonality of X. So this is the minimum of all integers C, so that X is covered by a family of curves of gonality equal to C. So there exists a curve of gonality equal to C passing through a general point of X. And of course, another invariant that people like to look at for curves is the genus. So we can talk about the covering genus of X. So this is defined in the analogous way, except we look for families of curves of geometric genus. We look at the geometric genus of curves passing through a general point. So it's a minimum G, so there exists a curve of geometric genus G. So geometric genus means the genus of the normalization. If the curves might be singular, so you look at the genus of the smooth model passing through a general point. Okay, let me see. Now, let's see. I'm going to do it just a little bit for the moment. And so these measure the deviation of X from being what's called uniruled. So the covering genus of X, the covering gonality of X equals 1 if and only if the covering genus of X equals 0, if and only if X is what's called uniruled. So let's say X is birationally covered by, so it's what's called uniruled, covered rationally by Y cross P1. So in other words, it's covered by a family of curves parameterized by Y. So this is what people in algebraic geometry called uniruled. Okay, and of course there's some relations among these. So the degree of irrationality, in general, the covering gonality of X is less than or equal to this degree of irrationality, because imagine that you've got a covering X. You found a covering from X to Pn of a certain degree, of degree 7. Well, if you look at the preimages of lines, that's going to give you a family of curves covering X, and each of those curves is exhibited as having a degree 7 map to P1. So in general, the covering gonality is less than or equal to the degree of irrationality. Now, it's also, again, well known in Riemann surface theory that if you have a curve of genus G, you can always express it as a branch covering of P of the Riemann sphere with degree at most roughly G over 2. It's G over 2 plus a little bit. So what that says is that the gonality of X, is less than or equal to 1/2 the genus. I'm not going to worry about the constants. It's like the integer part of G plus 3 over 2 or something like that. But in any event, it's essentially half the genus. Okay, and so the kind of question I want to discuss in the first half of the talk is how to control and compute these. So how to control and compute these. So question, compute these. Okay. Well, what's the first idea? What's the easiest way to tell that a variety is irrational? Why is an elliptic curve not rational? Well, it's because it carries non-zero holomorphic forms. So in general, if you look at the top dimensional holomorphic forms, the holomorphic n0 forms on a variety, that's a birational invariant. And on the other hand, projective space has no holomorphic n0 forms. So if you have a variety that carries top dimensional forms, holomorphic forms, it can't be rational. So the first idea would be to look at holomorphic forms. But of course, it's not, if you want to sort of control how irrational it is, you should look at sort of how positive it is. So the first idea is to use positivity properties of the canonical bundle. So these should give, if the canonical bundle is positive in a suitable sense, this should give obstructions, this should force these measures of irrationality to be pretty large. Now, what actually do you, so then in what sense do you really want the canonical bundle to be positive? And it's going to turn out that this is, the way you want to measure positivity of the canonical bundle is how many points it can separate. So let me just put this, here's the sort of yoga. That if the canonical linear series separates many points, then this will force these, this will give lower bounds on these invariants. Okay, and separating point means that you should more or less be able to, to say it separates 6 points means roughly that you should be able to find given any 6 points, you should be able to find a canonical, a holomorphic n form with kind of prescribed values at those points. So let me give you sort of an example. Let me give an example of how this procedure goes. And I'm not, there are a lot of names that come up here, so I'm going to use abbreviations. This was really, the first paper in this area was by Bastianelli, Cortini, and Dupuy, but I think the ideas go back to Parola. So let me explain how this works in a simple case, how this yoga works. So suppose you have a covering, a rational covering. I'm going to just, okay, suppose you have, suppose you're given a rational covering x from x to Pn. So it might not be everywhere defined. It's just a rational homomorphic map. Okay, then there's a trace map on n0 forms. Then you get a trace map, the trace of f, from the space of n0 forms on x to the space of n0 forms on Pn. There's nothing special about Pn here. Namely, you basically, if you're given an n0 form on x, you basically average it over the fibers, and that turns out to be a well-defined n0 form on Pn, so on the target. So so the way this works is that so for a general point y in the target, I'm not using at the moment that the target is Pn. You take the trace of f of omega. So this is supposed to be an n0 form on the target, and you just average, or you don't even, let's just add up. So you average the value of f at all the points of the preimage. And this turns out to give you a well-defined N0 form on the target. Okay, now let me see how this, let's see. Okay, so this is very confusing. I gave a talk on these things in Paris in the, whoops. One at a time, is that it? Okay. Okay. But now, okay, so but now the point is that no, just a little bit. Okay. But now, of course, the point is that, as we've said before, Pn has carries no n0 forms, right? The hn0 of Pn is 0. So let me finish erasing, and then I'll okay, but we know that hn0 of Pn is 0. So so what this means is that for any n0 form on X, its trace must be 0. Now, what does this mean geometrically? What this means is that if you can find an omega that vanishes at all but one point of the fiber, all but one point of the preimage, all but one point of the preimage for a general Y, then it must vanish at the remaining one as well. Right? Because if you found a form that vanishes at all but one point of the preimage and it didn't vanish at the remaining one, when you added up its values over the fiber, it wouldn't trace to 0. So this is a kind of a geometric condition this is a geometric way of sort of expressing the a geometric positivity condition on the canonical series of X. And so what comes out of this? So the simplest application of this is for hypersurfaces. So I'm going to just state a rough form. This is due to, they're more precise results. Many people, BCD, there's a paper with Bastianelli, Depoy, BDE, Ein, myself, and Brooke Ullery, and there are many other papers as well. So this works very well. This sequence of ideas works very well for hypersurfaces. So let me just tell you asymptotically what happens for hypersurfaces. So let's consider a smooth hypersurface XD in Pn plus 1, a hypersurface of degree D. And I want to fix n. I'm going to give just an asymptotic statement. So I want to fix n, fix the dimension, and then let the degree go, ask what happens asymptotically degree. Okay, and then the claim is that for fixed n and very large degree, then you can work out asymptotically. It's very clear what happens to these invariants. So let's see. So what happens? So the degree of irrationality as a function of D, okay, the degree of irrationality as a function of D is asymptotic to D. The covering gonality as a function of D is asymptotic to D, and the covering genus as a function of D is asymptotic to D squared over 2. And you can see that this, so for example, if you take a hypersurface of degree d and you just project that to Pn, that's going to be a map of degree d. A plane curve has gonality d, well, d minus 1, and genus d, roughly d squared over 2. So these you get by taking plane sections. So the asymptotic picture is very simple, and I can even more or less prove this for you. So what's the proof, in a word? So the proof is that just that the canonical bundle of x is OX of d minus n minus 2, right, by the adjunction formula. So if you have a hypersurface of degree d, the canonical bundle is roughly O of d minus a little bit, and this separates d minus n minus 1 points, so that forces these invariants to be linear in d. So the asymptotic bounds are very, follow more or less immediately from that. Much more precise results are known. These have been computed for hypersurface, but I don't want to go into the. To get the precise results also involves a little bit of delicate geometry going back to this first paper of Bastianelli, Cortini, and Dupuy. So this works this idea of positivity of the canonical bundle works very simply for hypersurfaces, because you can just say, because you know what the canonical bundle is for hypersurfaces, you can say that it separates a certain number of points. Okay. Now, anytime you have a result for hypersurfaces, it's natural to ask for analogous results for complete intersections. So typically, complete intersections should be very analogous to hypersurfaces. So a natural question, and this was going to be one of my first problems I proposed, is let's consider a very general complete intersection of hypersurfaces of degrees d1 through de in Pn plus e. So instead of a hypersurface of degree d, take the transversal complete intersection of hypersurface of degree 1, d2, all the way up to de. Now, the canonical bundle, the positivity of when you sort of look at the adjunction formula, this grows linearly in the sum of the degrees. But you would expect a multiplicative bounds on these things. And this was one of my favorite problems. So I was going to say, as a problem, can you find multiplicative bounds? But I was very happy to, this Monday, the evening of the first day of the conference, somebody sent, I got a preprint actually solving this problem. So this is very nice. So, let's see, Chen, Church, there is some earlier work. But so now this is, I haven't really absorbed what they've done yet, but they've actually solved this problem. So they've given multiplicative bounds. So this is a very nice multiplicative bounds. So let me say they've given bounds on these invariants that grow like the product of the degrees. Given bounds on these invariants that grow like, that grow like the product of these degrees, d1 times de. So that's very nice. So now I think, but this isn't obvious. This you don't get just by using the formula for the canonical bundle. But this is a very nice, this is a very nice piece of work. So I think for hypersurfaces and complete intersections, this story now is pretty clear. Now there, I don't know. Okay. Now there's as Janos Kolar taught us a few years ago, not a few years ago, maybe 30 years ago, there's another situation where you can use the presence of top-dimensional forms to study rationality, and that's for final hypersurfaces. So, okay, so let me say a word now about Fano hypersurfaces. So let's now consider, a very general hypersurface. I guess I'll write it like this: n plus 1 minus e in Pn, n plus 1. So a hypersurface of that degree with e positive. And so we want to sort of, this is the range where, so we want to, this is the range where rationality questions become very delicate. Now, of course, these are rationally connected. So there's no question about the covering invariants. So, but the question is, are they rational, or can you say anything about the degree of irrationality? And so what Kolar observed is that you can use the presence of top-dimensional forms to study this question. Now, that, to a complex geometer, that looks a little bit weird, right? Because, of course, a Fano hypersurface doesn't carry any holomorphic N0 forms. But what Kolar realizes is that if you go to characteristic P, to positive characteristics, under happy circumstances, you can deform X to a variety that's a branch covering of projective space, and because of prime degree and prime power degree, and because you're in characteristic P, these coverings can carry non-zero top-dimensional forms. And so that means that you can deform, what he showed was that you can deform X in such a way that it deforms to something that carries top-dimensional forms. That limit thing can't be ruled. And then Kolar used properties of it, limiting properties that if your family of ruled varieties, the limit has to be ruled, to show that there are many hypersurfaces in this Fano range. It must be irrational. So this was a very nice idea going back to the in the mid-90s, and then Chen and Stapleton had the nice idea to try to use similar ideas to bound these degrees of irrationality. So what they showed is that, again, using these deformations to cyclic coverings in characteristic P, that for fixed, if you fix E and n very large, the degree of irrationality grows like at least like constant times square root of n. So the degree of irrationality is at least going to infinity for a very general, did I say very general? Yeah, for a very general X. So this is already, so as I say, Kolar had shown that there are many very general hypersurfaces in this range where these are irrational, but this gives a nice quantitative improvement of his result. A natural question is, so this result was quite specific to these hypersurfaces. So a natural question here is, can one say anything about other Fanos? So I don't have any. Okay. Okay, so that's hypersurfaces. So I think for hypersurfaces, the situation, I guess, is pretty good. So where are these? So again, all these results so far, one way or another, involve canonical forms, involve studying sections of the canonical bundle. So what's the situation where these questions become most delicate? Where those would be varieties with canonical, so k-trivial varieties, so varieties with kx trivial. Okay. So let me start. So of course, if you have a variety whose canonical bundle is trivial, you don't have many holomorphic forms to work with. So here people have used other methods. And as you might think, the results are less clear. So let me start with an example in the case of surfaces. So here I think one has here the picture is what's known and expected is kind of the most clear. So let's consider the two families of surfaces, canonical trivial surfaces. So I'll let A sub D be a very general abelian surface. Abelian surface with a polarization of type 1D. So it should of type 1D. So it's a abelian surface that carries an ample line bundle of this type. And then the other family I want to look at are K3 surfaces. So let's let SD be a very general K3 surface of genus D. So with the polarization of degree 2D minus 2. So this would be a very general K3 surface of genus D. Okay, so let's see. T2 goes up. And T1 comes down. Yeah.
What do you mean of type 1D?
So if on a abelian variety, you take a polarization, it's given, there's an integer value, a line bundle on a abelian variety gives you an alternating integer value 2 form, right? And so you diagonalize it so another way of saying this is that it should have, it should be, I guess, degree 2D, and it should have D sections or something like that. So it's just it's the matrix, the diagonal matrix giving the polarization. Okay. Okay, so now here one can kind of just by hand see what the covering invariants are. So this is kind of fun classical geometry. So first of all, let's do the case of abelian surfaces. So I first of all claim that the covering genus of A is equal to 2. So let's see, why is that? Well, if you take a principally polarized abelian surface, that's the Jacobian of a curve of genus 2. And once an abelian surface contains a curve of some genus, then you can translate it around so it's covered by curves of those genus. So this is clear for principally polarized abelian varieties. That's type 1,1, but a 1D is a quotient of a 1,1 polarization. So any abelian surface contains lots of curves of genus 2, and therefore its covering gonality, a curve of genus 2, is hyperelliptic, so its covering gonality is equal to 2 again. What about K3 surfaces? Well, okay, so it's a classical fact that a K3 surface has a G-dimensional, if G is less than D, it has a G-dimensional family of singular curves of genus G. So in particular, it's a classical fact that a K3 surface has a one-dimensional family of singular elliptic curves. And so this is again, so the covering genus is 1, and so again, the covering gonality is 2. So there's no problem about what the covering invariants are. But the more interesting invariants are these degrees of irrationality. So I would have expected that the degree of irrationality of these abelian surfaces grows with D, but it turns out that's not true. It was shown by Chen and then also by Olivier Martin that any abelian surface can be expressed as a branch covering of P, rationally a branch covering of P2 of degree at most 4, and in most cases it's equal to 4 for most D. So strangely enough, these don't depend on the degree of polarization. Okay, what about K3 surfaces? So here, this is one of the first surface question where one gets into it's rather unknown. So here's a problem, and again, I think this is people have worked pretty hard at trying to do this. So the question is, if you take a general K3 surface of genus D, does its degree of irrationality go to infinity with D? So is it true that the degree of irrationality of SD goes to infinity with D? So at the moment, that seems to be completely open. But there is one funny thing. You might maybe expect it to grow linearly in D, but that's not true. So Stapleton showed that it can grow, that the degree of irrationality is at most a constant times the square root of D. So it can't go, it doesn't have to go linearly in D, but you can, as far as one knows, it goes to, one expects it to go to infinity. And then there's been some work by Federico Moretti and some others giving some lower bounds in low genus. Okay, what about higher dimensions? Well, obviously, as you would think, less is known. So in higher dimensions, let me see, okay. So the case that people have looked at the most is a billion varieties. So let's let A be a very general a billion variety of dimension n. And again, I should fix some polarization so I can talk about very general, but I'm just going to talk about the covering invariant so it doesn't matter. So let's see. So Pirola, building on work of Chiliberto and Vera and others, showed that if n is at least 4, then the covering genus of A is at least what? It grows quadratic, is at least quadratically n over 2. So it's n squared, n choose 2. So it's roughly at least n squared over 2. So you can get a quadratic bound in n just by counting moduli, but I think that gives you n squared over 4 over 6. So this is a, okay, so again, what the genus of an abelian variety means is it's the least genus of a curve on your abelian variety. Now, as usual, the covering gonality is much more subtle, and this was studied more recently by Claire Voisin and Olivier Martin. And the upshot of their work, using Chow theoretic methods, and the upshot of their work is that there's at least a linear bound. So Voisin and Martin showed that the covering gonality is at least roughly, at least it's linear in n. So what is it? I think it's n over 2, something like that. Okay, so this is, I say, they studied the Chow group of zero cycles. Okay, these invariants are getting big, but the funny thing is that I've asked around and nobody seems to have any idea if these are anywhere close to being sharp. And in fact, there's this fun problem that's been circulating. So I don't claim any originality for this problem, but so let's look at the question is what's the right value for these things? So supposing I give you a very general abelian variety of dimension n, what's the least genus of curve you can find on that abelian variety? Well, you know, what can you do? You can take complete intersections of multiples of the theta divisor, but that gives you exponential bounds. So as far as I know, it's unknown whether or not the upper bounds, whether you can actually construct examples where these invariants are polynomial n. So the problem here is, are there bounds that are polynomial in n? So for example, if I give you a general abelian variety of dimension n, can you find a curve on that abelian variety whose genus is given by a polynomial in n? Or do you have to go to things like n factorial, which is what you get for complete intersections, for obvious complete intersections? So this is, I think, this is a question that's come up in various areas. I don't have any ideas, but I think it's a fun question. I was planning to say something about hyperkähler manifold. Oops, wrong button. So Claire Voisin has some interesting ideas about what Claire did is she looked at hyperkähler manifolds, and instead of looking at just these invariants for curves, she looked at invariants for curves that are organized in a kind of a nice way. So her idea was take a hyperkähler manifold and imagine that it's given by, you have a fibration in curves of that thing. So you take your hyperkähler manifold of dimension 2n and you map it to a variety of dimension 2n minus 1. So it's fibered by curves, and she has some bounds for the geometry of the curves and the fibration. But I think in the interest of time, I will skip over that. Okay, now I want to talk about sort of a different set of ideas, I mean related, which are what we call measures of association. Okay, so what is that all about? So this is so this is work with joint with Olivier Martin. And the idea is this, that what we were looking at up to now is you take a variety and you're asking how close it is to being birationally isomorphic to projective space in various ways. So what you might, more generally, the idea here is we start with two varieties of the same dimension n. You know, irreducible let's say smooth irreducible projective varieties. And now we want to ask how close are these varieties to being birationally isomorphic to each other. So how do we measure the deviation? How can we say something about the deviation from being birationally? So we ask how much do these differ birationally? Just like the previous invariants were somehow asking how much does a given variety differ birationally from projective space. So, okay, so what's the natural way to look at this? So we'll look at correspondences between x and y, and we'll try to study the kind of birational complexity of these correspondences. So let's consider correspondences. So I'll have an irreducible projector, let's say smooth projective variety z of dimension n, and I'll take a map from x, A from z to x, and B from z to y. And let's see, I want to say that z is irreducible of dimension n, and A and B should be generically finite, and therefore surjective. And of course, everything's going to be birationally invariant, so I could let these be rational maps, but then I would just resolve the indeterminacies. Okay, so let me just start what the invariant that is the sort of analog of this degree of irrationality. So let's define the correspondence degree between x and y to be the minimum over all these z of the product of these two degrees. So the minimum over all z of the degree of A times the degree of B. Okay, so when is this correspondence degree equal to 1? Well, that happens if and only if degree of A and degree of B is 1. So this correspondence degree is 1 if and only if x and y are birationally equivalent. So let's see. So correspondence degree, okay, let me put it here. So let me move this up a little bit. Okay, so this number is equal to 1. This is equal to 1 if and only if they're birationally isomorphic. Okay, so this really measures the failure to be birationally isomorphic. Now, how do you construct, if I give you two random varieties, how do you construct correspondences between them? So I claim that there are always some kind of silly correspondences that you can define, you can find between two random varieties of the same dimension. Namely, let's take, given x and y, let's write them as coverings of Pn. You can make them rational or regular coverings. To simplify, I'll pretend that they're, so consider coverings, rational coverings. So I'm going to say I can take x in any variety, right? I can write x as a covering of Pn, and I can write y as a covering of Pn. And if you like, you could make these rational. I don't really care. Okay, so obviously I can do this in lots of different ways. But then what I can do, so let me draw a little picture here. So I have x as a covering of Pn. No, this is beta. I have y as a covering of Pn. And then I can take the fiber product. So I can look at pairs, a point in x and a point in y, and this with the same image. So I take z to be an irreducible component of the fiber product. So take z to be an irreducible component, a suitable irreducible component of x cross Pn over y. So then I'll get a map A here and a map B there. So z is just basically pairs of points with the same image, or it's some irreducible component of that. Now, certainly what's true is that the degree of A is less than or equal to the degree of alpha, and the degree of B is less than or equal to the degree of beta. So what that means is that so what that means is that the product of these two degrees is less than or equal to the product of the degree of beta times the degree of alpha. So what that means okay, so what that means is that the correspondence degree is less than or equal to the product of the degrees of irrationality. Okay, so what this means is that the correspondence degree between x and y is less than or equal to the product of the degrees of the irrational. And the intuition, so I always get some I can always construct silly correspondences. So the intuition is that if the equality holds, and especially if this is only the minimal correspondences arise like this, somehow that indicates that x and y are birationally independent. So somehow the kind of independence case is when these are the minimal constructions. So for example, it's a nice exercise to show that if you take very general curves, very general curves of genera gx and gy, then we're in this kind of situation. So then the correspondence degree x and y is just the product of the gonality. So, and the minimal things are the minimal correspondences are fiber products. And again, this is just what you'd expect. I mean, it's kind of well known from the theory of Riemann surfaces that if you take two random Riemann surfaces, there are no interesting correspondences between them. So Okay. Yes, yes, yes. So, right. So, if so, Claire has some examples, and I think John Autumn also. So, if this says that the correspondence degree between x and Pn is less than or equal to the degree of irrationality, but there are examples where it's strict. But Claire asked the questions: can you find examples where a family of examples in the given dimension where the ratio goes to 0? And I think that's not known. Yeah. Okay. So, another remark to be made is that by this kind of fiber product construction, you see that this invariant satisfies a multiplicative so remark, or maybe a little proposition, is so this satisfies a multiplicative triangle inequality. So what this means is that the logarithm of the correspondence degree defines a metric on this set of all birational equivalence classes of varieties of fixed dimension and so an interesting question, which I don't even know. So this means that this set of birational equivalence classes is some kind of discrete metric space. And as probably people here know much better than I do, there are various invariants you can attach to discrete metric spaces. So the question is whether this is a curiosity or whether there's some interesting geometric thing about this. Interesting? So is it an interesting metric space? I have no idea. I have no idea. So anyway, that seems like I have no idea. But anyway, it seems like it's a question, right? Again, one can, let me just, all the stuff we did earlier for hypersurfaces goes over without too much difficulty for pairs of hypersurface. So let me just state a little theorem here. If x and y, so if xd and ye in Pn plus 1 are very general hypersurfaces of degrees, I want them not to be too small, 2n plus 1, let's say 2n plus 1, then we're in this situation when they're kind of independent in this sense. So then the correspondence degree is just the product of the degrees of irrationality, and the minimal things are fiber products. So this is saying, as you might expect, that two random hypersurfaces have no unexpected correspondences between them. You can also ask what happens if you start with x and y of different dimensions. So there's a guy, Giovanni Passieri at Stony Brook, who's looking at this question. The thing to do is you would then take products with projective space to stabilize. And then you can look at different correspondences between varieties, different dimensions. So let me end by saying a word about these joint covering invariants. Okay, so again, we're given two varieties, and now the other kind of invariance we looked at for a given variety was we looked at families of covering of curves. We take our variety and we look at covering of curves. So the idea here is that what you can do is you can look at families of curves that simultaneously cover both varieties. So we can define then the covering genus of x and y. Well, I'm going to write genus so I don't confuse it with gonality. The covering genus of x and y to be just, I take the minimum over all correspondences z of the covering genus of z. So in other words, I'm looking at families of curves that simultaneously cover both x and y, and I do the same thing for analogously. So I would look at families of the least gonality of families of curves that cover both x and y. Now, so I want to give one example, and then I'll end with a sort of a tantalizing open question. So let's go back to this case of K3 surfaces and abelian surfaces, and so we can see kind of, it's fun to see what's happening there. So okay, so let's start with abelian K3 surfaces. So let's take S and S prime, very general K3 surfaces. Now remember I said that S and S prime are each covered by families of elliptic curves. But if any one-dimensional family of elliptic curves, as long as it's non-isotrivial, is kind of more or less a complete family. So in fact, you can convince yourself easily that you can find one family of elliptic curve that simultaneously covers both S and S. So here, the covering genus of S and S prime is equal to 1. So you can find one family of elliptic curves that covers both K3 surfaces simultaneously. Now, what about very general abelian surfaces? Well, as we said before, any abelian surface contains a curve of genus 2, and then you can translate that curve of genus 2 around, and you can cover it. But curves of genus 2 on an abelian surface, it's an old result of Perola, are rigid. So the curve of genus 2 that lives on A has nothing to do with the curve of genus 2 that lives on A prime. So you don't expect to find one family of curves that covers them both. And in fact, it's a nice result of Moretti and Passieri that the covering genus is 6. So although each of these things contains a curve of genus 2, there's not one. You have to go to genus 6 to find covering families. And then let me end by stating a kind of a problem for curves. So you would think anytime you have an invariant, the first thing you should do is you should look at what it happens for curves. So curves, let's say we have x and y, very general of generas gx and gy. So okay, so then what is this covering genus and covering gonality? So the covering genus of x and y, you're just asking what's the least genus of a curve that can be expressed as a branch covering of both x and y. And same thing for the gonality. So it's not hard. So a proposition, you get at least, you expect these things to be multiplicative. And so you check at least for the genus, so plus lower order terms is less than or equal to the joint covering genus of x and y. It's between less than or equal to something like 5/4 of the product of the genera. So at least you get lower order terms. But the weird thing is, it seems completely unclear. I mean, it's hard to believe that one can't answer this. I have no idea what is the joint covering gonality. So, joint covering gonality of two curves is we have no idea what it is. So the hope is that it should be, like it should grow like gx and gy, but have no idea how to prove a multiplicative bound. Now, Chen and Farkas and Ruji Yang have given some good estimates if you assume that starting with two curves, that you assume that the joint thing you get, the joint covering thing it sits in a fiber product. But so that amounts to some kind of dynamics being finite somehow. But in general, it's completely opaque what this is. And again, you can look at these things for hypersurfaces, but my time is up, and so I'll end there. Yeah, thanks.